Hello and welcome. Today we're going to be talking about Newton's law of cooling. So what we have here is an object, and it's going to have a with a temperature T of T. Okay, and the object, I'll just give an example of a turkey that just came out of the oven and it's hot. And it has a temperature T of T. Okay, so it just came out of the oven. We want to know, and the question then is, of course, what governs the time dynamics of T of T. Okay, and so the answer to that is Newton's law of cooling, one of Newton's laws, many laws, of course, which is effectively what we say is the rate of change of temperature decline, or temperature cooling. The rate of cooling is proportional to the temperature difference between object the object and its environment. Okay, so that's the law. Okay, and let's write down, if we can write down the differential equation that actually summarizes this law right here. So they say the rate of change, the rate of temperature cooling. So that's actually d capital T dt. Okay. We say it's proportional to the temperature difference, which means we'll have K being our proportionality constant. And then we're going to write T environment, TE minus T. Okay. Where K then is our constant of proportionality. And I'm going to, K is some constant, and then of course TE is the temperature of the environment. Okay, so a few caveats here. We need K to be a positive number. Okay, that's one of our caveats. And what we see here is that if for instance, examine T being bigger than TE. That means that TE minus T is negative, right? And if K is positive, then of course that means dt, d time, is going to be also negative, which is what we expect from reality. We want a hot object to cool to its environment. So we need this constant to be positive, and we need to be TE minus T there. Okay, so that squares with what we expect in reality. Okay, and the other thing to note is that TE could be a function of time. So it could be TE of T. And we can always imagine many scenarios where the environment actually changes temperature over the course of the day, of course. It gets hotter and colder. And we could be, for instance, measuring the temperature of our house as it tracks that temperature. So as you know, it might be a peak temperature outside, but because you've closed the windows, it takes a while for the energy to leave the house and heat up. So typically your house in the middle of summer will be hot well after the sun goes down before it cools down again as you go. Another important thing to note is that this isn't just cooling. It could be heating as well. Okay, so now let's get and actually write down and do an example of this type of differential equation. So let's solve a differential equation. So again, we're going to have our turkey. And so we have our turkey like that, and it's hot. And at time 0, our turkey, we're going to pull it out of the oven. And it's going to be 180 degrees. And that'll be out of oven. Okay. And the environment then, we'll say, is 75 degrees. All right, and we want to know about the cooling. Okay, and then suppose, okay, so the question then is, what is K? Well, maybe we don't know what K is, but we actually have 2 pieces of data. Suppose that, okay, after t equals 20 minutes, we observe that t at 20 minutes is now down to 140. Okay, so we've had some cooling. All right, so the question then is, can we find K? Find K given we know t at time 0 and also t at 20 minutes. Okay, and we also know, of course, that the cooling is governed by Newton's law of cooling. So let's write down the differential equation. dt is equal to K. We put our 75 in there, and that's, of course, our environment's temperature, minus T of T, which is unknown. This is a first-order linear equation. We could also solve it as a separation of variables problem, but I'll do a first-order linear. Okay, so we're going to move things into the form, and we have a plus KT is equal to K times 75. All right, so now let's solve this differential equation. So of course our P of T in the format we've used in previous lecture videos is going to be K, right? And that means my integrating factor, rho of T, is going to be e to the antiderivative of P of T dt, the antiderivative of P of T, which is going to be e to the antiderivative of K dt, and that's going to be e to the kt. All right, so we're going to multiply both sides of the dE by that rho, and then we get, now if you're not familiar with if you're not familiar with first order linear equations, go see some of my other videos on that. But we'll just skip right to the point here. We're going to multiply rho by t prime plus k rho capital T, and then we put k times 75 times rho. So we've multiplied this equation right here, everything by rho. Of course, this can be rewritten as a product rule. So we're going to take the derivative of this product of t and rho together, and that is on the right-hand side is the same. Okay, now we integrate. And we get k over 75. We're going to integrate this function here, and when we integrate it, we're going to get a e to the k t all over k plus c. The k's cancel, and over here we're just left with t times rho is equal to 75 e to the kt plus c, Okay, and then all we have to do is solve for t, and we get 75 minus c e to the negative kt. So that is my general solution. So let's go to another page. I'm going to rewrite that general solution. T of t is equal to 75 minus c, which is our undetermined constant, that's our free parameter, minus kt. All right, so we said that at time 0, we knew the temperature was 180. All right, we'll set that equal. That's 75 minus c e to the k t. So and that's 0 right there for t. Okay, and so then what we get out of it is that it's going to be 180 minus 75 is equal to c. And that value is, if I'm looking at it correctly, 80 plus 25, so 105. Okay, so that was using one piece of our data. Right, so now we know that we have T of t is equal to 75 minus 105 e to the negative kt. We still have that unknown k parameter, but remember we have that other fact. We know that at 20 minutes that our temperature is going to be 140 degrees. That's what we said. So let's write that down. 75 minus 105 times e to the k, negative k, times 20. All right, so now, of course, we solve for k. 75, so we have 40 plus 25, that's 50, 65. Okay, so what we have then is 65 is equal to negative 105 e to the negative k times 20, and then we divide by negative 105, so we get 65 over negative 105, and that's equal to e to the negative k 20. And then it's worthwhile here to I think I made a mistake there. We should have put a plus there, right? Yes, we should have put a plus there. That makes sense. That's better. Sorry, I made a little sign error there. Okay, so now we go further. We take the logarithm of 65 over 105, whatever that value is. I can't do the arithmetic right here in my head. And that's going to be equal to negative k times 20. Because we have a negative value, that can just flip the logarithm, so we actually get k is equal to 1 over 20 times the natural log of 105 over 65. Okay, so that's our value, our computed value for our rate constant. So then the final solution, T of t, is going to be 75 plus 105 times e to the k, and I won't write that out again, negative k times t. All right, so what is this graph? Well, I'd like to just draw quickly the graph of this function. All right, so it starts off at 180 degrees, and it's going to eventually go back to 75 degrees, little dotted line there. And there's just a decaying exponential as it relaxes down to that room temperature. So, and then of course at around at 20 minutes, we know that it's going to be 140 degrees. Okay, so hopefully that can clear up, that can illuminate some of the nature of cooling, how that cooling in general involves exponential decay. Okay, an exponential decay type process. So, of course, there's more or faster cooling at the beginning and slower cooling at the end as it equilibrates to room temperature. All right, thank you very much.